Good morning, students. Welcome back to our physics classes. During the last class, we have started with the concept of rigid body, and we have defined a rigid body, and we have seen some terms related to that rigid body. That is, what kind of movements a rigid body can have. It can have both the translatory motion as well as rotational motion. So for rotational motion, which is responsible for its rotational motion, that is the torque. The term which is responsible for the rotational motion of a body, rigid body, is torque. And we have defined its equations of motion. Equations of motion from we transferred equations of motion from linear motion into rotational motion. So during rotational or using rotational aspects, we have defined the equations of motion that we have stopped in the last class. Where we have stopped in the last class. Okay. So today we are going to define another aspect of rotational or another term related to rotational motion. That is, suppose when you are having an object and that object is acted upon by a force. A force is acting on that object and that object is getting displaced. You have to do a work. Why? Because you have to overcome its inertia. What is inertia? The tendency to change its state, or the tendency to resist its displacement, in this sense. So whenever you are having a rigid body and you are trying to rotate it with a torque, so there is a tendency of that rigid body to resist that torque acting on that. There is a tendency of that rigid body to oppose the torque acting on that, which means it has a tendency to oppose its rotation. And that property is known as moment of inertia. That is known as moment of inertia. The term is known as moment of inertia. See, from the term itself, it is clear that it is somewhat related to inertia. What is inertia? Resistance to the state change, or opposed to the change in state. See, this moment of inertia, I already told you the moment of linear aspect is rotational aspect. So moment of inertia, that means rotational inertia. Rotational inertia is known as moment of inertia. And suppose you are having a rigid body. A rigid body is capable of rotating about this axis passing through the point P or point O. Origin is point O. It consists of three particles. One is here, another is here, and the third one is here. So this is distance R1, this is distance R2, and this is distance R3. So the moment of inertia of this rigid body is calculated as, suppose here the mass is m1 and here the mass is m2 and here the mass is m3. So the moment of inertia is denoted by capital I is equal to m1 r1 square plus m2 r2 square plus m3 r3 square. That is moment of inertia of a particle. Moment of inertia of a particle is single particle. Moment of inertia of a single particle is the product of the mass of that particle and the square of the distance from the axis of rotation. See, m1 is a particle. M1 is a particle whose distance from the axis of rotation is r1. So moment of inertia of m1 is m1 r1 square. For the second particle, similarly m2 r2 square. For the third, m3 r3 square. So the total moment of inertia of the system is the moment of inertia of the particles which constitute in that system. So the total moment of inertia is the sum of moments of inertia of the individual particles in that system. That is the total moment of inertia of a system. So in general, you can write it as I is equal to sigma m r square. Sigma m r square. Or you can find out m I r I square. Anyhow, so that is the moment of inertia of a rigid body. If it is a there is no this kind of continuous distinct particles, it is a continuous mass distribution, so it is given by I is equal to integral r square dm. As usual in the case of a continuous charge mass distribution, you can get the moment of inertia as I is equal to integral r square dm. So r is the distance from a small mass dm. So that is I is equal to integral r square dm is the moment of inertia of a continuous mass distribution. Otherwise, you can use this equation I is equal to sigma m r square. Okay. So that is moment of inertia. I already told you moment of inertia is the tendency of the system to oppose any kind of rotational motion. So it opposes the torque acting on that. If a torque is acting on a object or a rigid body, the torque is opposed by this moment of inertia. And the moment of inertia is very similar to mass in our linear motion, translatory motion. What mass plays the same role played by moment of inertia in the rotational motion. That means if moment of inertia, if mass is more force is required. Similarly, if moment of inertia is more torque is required. Okay. So this moment of inertia plays a important role in our daily life. When you are riding a bicycle, when you are braking, the wheels will rotate for some time. That is due to this moment of inertia. As it rotates, if the state changes, it opposes its motion. That is why, it opposes that torque acting or the force acting. So that is why, see, for a wheel, say bicycle wheel, the whole mass is most of the mass is concentrated on its ring, and the ring is connected to the axle by spokes. So it possesses a large moment of inertia. And when you are riding, it is rotating, and when you are braking, the rotation is getting disturbed. That is opposed by the large moment of inertia. That is why for a short span of time, it even rotates when you are braking the wheels. So that is a daily life experience of this moment of inertia. So I already told you this moment of inertia is the property of a rotating body. Moment of inertia of a rotating body. So if you are having a rigid body, that rigid body can rotate about an axis. So when from this equation it is clear that when the point of rotation, the axis of rotation changes, R1, R2, R3 are getting changing, which means moment of inertia depends upon two factors. One is the mass and the other is the distance from the axis of rotation. So whenever the axis of rotation changes, moment of inertia changes. Whenever the mass changes, moment of inertia changes. So moment of inertia can depend upon two factors. One is the axis of rotation and the other is mass. The other is mass and one is the axis of rotation. So the same object can different the moment of inertia depending upon the position of axis of rotation. So suppose this is a rod, and this rod can rotate like this. Is it? When I am fixing at the center, it can rotate about its point. Is it? When I am rotating here, it can rotate either like this in the same plane, or it can rotate like this, vertical plane. So depending upon the nature of rotation or the nature of axis of rotation, the presence of axis of rotation, the moment of inertia is changing for the same body. So we'll come to that. Anyhow, to find out the moment of inertia of a rigid body, we can make use two theorems. Only the statements of those two theorems you have to learn. In the coming topics, only the equations or the definitions only you have to take. That only there in your syllabus, and derivations are not required. Derivations are not required, but only the statements and its definitions, statements, or the equations only you have to learn. So to find out the moment of inertia of a rigid body, we have two theorems. I already told you, depending upon the rotation and axis of rotation, the same body can have different moment of inertia. So, according to the situations, you can either use one of these laws to find out the moment of inertia of a rigid body. So, we can start with those theorems to find out the moment of inertia of a rigid body. Okay, so these two theorems are one is parallel axis theorem, and the other is perpendicular axis theorem. Perpendicular axis theorem. So these are the two theorems of center of mass, moment of inertia, to find out the moment of inertia. Suppose you are having a rigid body, and this rigid body has its center of mass. Or, first of all, you can consider it is capable of rotating through an axis I dash. Okay, this is a rigid body which is capable of rotating about this axis I dash. Okay, so it can rotate. It is parallel to. It is rotate about this axis I dash. Now, it has its own center of mass. It has its own center of mass. That rigid body has its own center of mass. You are having another axis passing through this center of mass. This is CM. Okay, CM is the axis passing through the center of mass. It can rotate about the axis passing through the center of mass also. So here you are having two parallel axes. Parallel axis of rotation, and these two are separated by a distance a. The parallel distance between these two axes is a. So parallel axis theorem says that moment of inertia of a rigid body about any axis, moment of inertia about any axis is equal to the sum of moment of inertia of an axis passing through the center of mass plus product of mass of the body and the parallel distance between these two axes. I repeat, moment of inertia of a rigid body about an axis about any axis parallel to an axis passing through center of mass. Moment of inertia about any axis parallel to an axis passing through the center of mass is the sum of moment of inertia about the axis passing through the center of mass plus the product of mass into mass and square of the distance between these two parallel axes. So we can say that moment of inertia about I dash is equal to ICM plus M into A square. So I dash is any axis that can be reversed. Suppose you are having another axis here which is at a distance b from the axis passing through the center of mass. So suppose this is B dash. So IB dash is equal to ICM plus M into B square, where B is the distance between those two axes. Those two axes means parallel distance from the axis passing through the center of mass to that particular axis. So, moment of inertia of a rigid body about any axis is the sum of moment of inertia about an axis passing through its center of mass plus product of total mass and square of the distance between these two axes. That says the parallel axis theorem. Its proof is not required, only this statement you have to learn. Okay, only the statement you have to learn. So that is parallel axis theorem. Now, we can define perpendicular axis theorem. We can define perpendicular axis theorem. For that, consider you are having a rigid body of a plane lamina. Lamina means a surface. So you are having a plane lamina and it is passing, it is capable of rotating about an axis, passing through or passing perpendicular to its plane. Can you imagine that? Have you seen puppet? So you take a puppet and you are piercing a what we can say, a needle through its surface. So suppose this is that puppet surface and you are keeping a needle perpendicular to its plane and it is capable of rotating about that needle, is it? So suppose this is the needle then, and if it is passing through its surface, it can be rotated about this needle. So this needle is the axis of rotation and it is passing perpendicular to the plane of this surface or plane of this, perpendicular to the surface of that lamina. So similarly, this is the axis passing perpendicular to the surface of this lamina and it is capable of rotating. See, this can be rotated like this about this axis. Is it clear? Now you have to find out the suppose this axis is z dash, and you have to find out the moment of inertia about this axis. For that, you keep another axis along the same plane of this lamina, and suppose this is taken along x direction, x dash x, and this is taken as suppose this is y dash. This direction is taken as y dash, and this is z dash z. So this x, y, z are making three mutually perpendicular directions. See, this is a perpendicular axis about which we have to find out the moment of inertia. So simply it says that I y dash is equal to I x dash plus I z dash. What it means? Moment of inertia of a plane lamina about an axis perpendicular to its plane is the sum of moment of inertia about two perpendicular axes lying at the same plane of that lamina and meeting at the same point through which that third axis is passing through. Getting confused? Listen carefully. Moment of inertia of a plane lamina about an axis perpendicular to its plane. Is it clear? Moment of inertia about an axis perpendicular to the plane of a lamina, which is equal to the sum of moments of inertia of two perpendicular axes lying at the same plane of the lamina. See, x dash and y dash are lying at the same plane of this lamina and they are perpendicular to each other and they are meeting at the same point through which the third perpendicular axis is passing through. Now it is clear. Okay, so moment of inertia of any axis perpendicular to a plane lamina is the sum of moment of inertia about two axes lying in the same plane, meeting at the same point through which the third axis is passing through. It is not necessary that it should be in a circular lamina. It can be of any shape. It can be of any shape. Again, this is the perpendicular axis. So you can have two perpendicular axes, x dash and z dash, z. This is y dash. So again, y is equal to ix plus iz. That is the perpendicular axis theorem. So perpendicular axis, why the name comes from perpendicular axis? So that is, we are finding the axis passing perpendicular to the plane of this lamina, which is the sum of moment of inertia about two axes lying in the same plane, which are perpendicular to each other and meeting at the same point through which the perpendicular axis is passing through. That is perpendicular axis theorem. Why the earlier one we are calling as parallel axis theorem? Because there you are finding the moment of inertia about any axis which is parallel to the axis passing through the center of mass. Center of mass is fixed. So the axis passing through the center of mass is also fixed. So you can take any axis parallel to that axis passing through the center of mass. That can be easily find out as ICM plus m into a square, where m is the total mass of the rigid body and a is the distance between the axis passing through the center of mass to the required axis of rotation. In perpendicular axis theorem, perpendicular axis is passing through, passing in a direction perpendicular to the plane of the surface, and it is sum of moment of inertia about two axes lying in the same plane, perpendicular to each other and meeting at the same point through which the perpendicular axis is passing through. That is perpendicular axis theorem. So you remember the statements for parallel axis theorem and perpendicular axis theorem. This statement, mere statement, will not defines the perpendicular axis theorem, or that I is equal to ICM plus MA square will not defines the parallel axis theorem. So definition you have to learn along with these equations. So simple equations they are having. So in perpendicular axis theorem, I y dash is equal to ix dash plus I z dash, or simply I y is equal to ix plus I z, or in parallel axis theorem, I is equal to ICM plus MA square. So that is parallel axis theorem and perpendicular axis theorem. Okay, so that is moment of inertia. So the moment of inertia, I already told you, it's a property of a rigid body and depends upon two factors, mass and axis of rotation. So depending upon the axis of rotation, what are the moment of inertia of some special geometries, some special kind of rigid bodies we are defining, and you have to learn the equations for finding the moment of inertia of those geometries or those kind of rigid bodies. So first case is moment of inertia of a rod or a thin bar. I already told you this is an example for thin rod or a bar, and it can rotate at the center or at one of its end. So what will happen to the moment of inertia? That is that equations you have to learn. If it is rotating about an axis passing through its center and perpendicular to its length. So an axis is like this and it is rotating like this. So its moment of inertia is given by ml square divided by 12. If a rod of mass m and length l, it is rotating about an axis passing through its center and perpendicular to its length. So its moment of inertia is given by ml square divided by 12. And its derivation is not required. Only you have to learn that equation ml square divided by 12. ICM is equal to ml square divided by 12. And if it is rotating about an axis passing through one of its end, it is like this. It is rotating like this. Now it is given by ml square divided by 3. It is given by ml square divided by 3. If it is passing through the center of mass, that is center of the rod, and it is rotating ml square by 12. If it is capable of rotating about one end, then it is ml square by 3. So that is a thin rod or a bar. Then a rectangular lamina. Suppose this is a rectangular lamina and it is capable of rotating about an axis passing through its center like this. So what will be the moment of inertia? Its moment of inertia is given by m into L square plus B square divided by 12. M into L square plus B square divided by 12, where m is the total mass of the lamina, L and B are corresponding length and breadth of that lamina. Okay, m into L square plus B square divided by 12. That is the moment of inertia of a square lamina. Then, moment of inertia of a ring. Moment of inertia of a ring. If it is passing along the perpendicular axis, if it is, you know that this factor, it is capable of rotating about the perpendicular axis, then its moment of inertia is given by mr square. Its moment of inertia is given by m into r square, where m is the mass and r is the radius. If it is capable of rotating about any diameter, if it is rotating about any diameter, that means about any zz or xx dash, any of the axis lying at the same plane. You know it's a diameter. Diameter lies in its plane only. So whenever it is rotating about an axis passing through its diameter only, then it will become half mr square. About perpendicular axis it is mr square. About any diameter, that is half mr square. Okay. Then instead of a ring, we can consider a circular disc. If it is a circular disc and it is rotating about an axis passing through its center of mass, again a perpendicular axis. A circular disc is rotating about a perpendicular axis, then its moment of inertia is given by half mr square. For a disc, it is given by half mr square, where again m is the mass and r is the geometries are given in your textbook, and that equations also given in the textbook. You just remember those equations only. No need to go for the derivation, and you can just mock up that equations corresponding geometries. Okay, that is left to you. Nothing extra to explain there. So you just read that geometries. You just go to the geometries and its moment of inertia about different axes. That equations only. That equations you have to learn. Okay. Okay, so now some more topics are given in your textbook, but that topics are not in relation with our syllabus. It is not mentioned in your syllabus, but it is related to comparison of linear motion and rotation motion. So we can explain those content now, which means suppose you are having angular momentum. Momentum in linear motion, we are having the momentum as P is equal to m into v. P is equal to m into v. As a momentum is mass into velocity. In rotational motion, momentum is given by J, angular momentum. Angular momentum. Angular momentum, when you are converting all the terms from linear motion into rotational motion, this P can be replaced by J. P is the linear momentum and J is the angular momentum. What is m? Mass. What is the rotational equivalent of mass? That is moment of inertia I. What is velocity? Velocity is changing into angular velocity. So that is I omega. J is equal to I omega. So J is equal to I omega. J is equal to I omega is, J is equal to I omega is the relation between linear momentum and angular momentum. Linear momentum and angular momentum. Now you are having force. F is equal to mass into acceleration. Force can be replaced by torque. Mass can be replaced by I. A can be replaced by alpha. Tau is equal to I alpha. Tau is equal to I alpha. Is it? Tau is equal to I into alpha. And again, we can have, so this is the relation between linear momentum and angular momentum. This is the relation between force and torque in terms of moment of inertia. That is important. In terms of moment of inertia, you are deriving an equation, I mean, we are defining an equation between P and J and F and tau. P and J and F and tau. And kinetic energy. Kinetic energy is K is equal to half mv square. That can be replaced by half into I into omega square. Is it? Where m can be replaced by moment of inertia and velocity can be replaced by angular velocity. Velocity can be replaced by angular velocity. Okay. Then we have another relation F. F is equal to dp by dt. F is equal to dp by dt. And F you can replace by tau. So, tau is equal to d by dt of what it will come? P you can replace by j. dj by dt. Tau can be replaced by dj by dt. Okay, you can easily derive this relation. F is equal to dp by dt and tau is equal to dj by dt. You know, tau is equal to I into alpha. That we have already written I into alpha. What is alpha? I into d omega by dt. Alpha is rate of change of angular velocity. So J is equal to I omega. J is equal to I omega. So what is dj by dt? dj by dt will be I into d omega by dt because I is constant. So when you are comparing these two equations, you can write tau is equal to dj by dt. Simple relation. So these are the simple relations. That is why it is not mentioned in your syllabus, but it is given in the textbook. So you remember this equation. Every equation in linear motion that can be easily converted into rotational motion by changing linear term into angular terms. That we have seen in the last class by deriving the equations of motion. Whatever notations we are used in linear motion that can be taken by notations in the angular motion so as to derive that equation. So that is our relation between linear aspects and rotational aspects. Okay. Okay, so that is the relation between linear motion and rotational motion. So in linear motion we are defining linear momentum conservation. What it says, if an external force is absent, the total momentum of the system remains constant. Similarly, here we can define angular momentum conservation. Angular momentum conservation says that in the absence of an external torque, the angular momentum of a rotating body remains constant. Similarly, very similar way we define the linear momentum, we can define the angular momentum conservation also. In the absence of an external torque, the angular momentum of a system remains constant. That is angular momentum conservation. Okay. So that's all for today. So we have defined moment of inertia and we found the equation for moment of inertia and we found moment of inertia for different axis of rotations. Whenever axis of rotation changes, mass changes, moment of inertia changes. Then parallel axis theorem, perpendicular axis theorem, moment of inertia for some bodies, and through moment of inertia we are converting linear aspect into rotational aspect and law of conservation of angular momentum. Okay, so that's all for today and we will meet in the next class.